There is a simple white powder you can buy at almost any hardware store for just a few dollars. Most people walk past it every day without realizing what it can do. When applied to a roof or wall, this powder can reflect nearly all of the sunlight that hits it, dramatically lowering the temperature of the surface beneath. In some cases, homes coated with it have stayed up to 10 degrees cooler inside during the hottest days of summer. No electricity, no complicated machines, just a basic material that humans have known about for thousands of years, and yet today, almost no one talks about it anymore. At first, that claim sounds almost unbelievable. A cheap white powder that can cool an entire home more effectively than expensive modern systems? If something that simple truly worked, you would expect to see it everywhere, on rooftops, on walls, across entire cities struggling with rising heat. Yet in most modern neighborhoods, the roofs are dark gray, brown, or black, absorbing the full force of the sun all day long. So the obvious question becomes impossible to ignore. If this solution has existed for so long, why isn't everyone using it today? Was it forgotten? Replaced by better technology? Or did something else happen along the way? To answer that question, we have to travel far back in time, thousands of years before air conditioners, before electricity, and even before many civilizations had written language. Because long before modern cooling systems existed, ancient builders had already discovered a surprisingly powerful way to fight the heat using nothing more than stone, sunlight, and simple physics. Thousands of years ago, long before modern air conditioning existed, people living in some of the hottest regions on Earth had already discovered a simple way to keep their homes cool. Across the islands of Greece and the sun-baked coasts of the Mediterranean, entire villages were covered in bright white walls and rooftops. Travelers who visit places like Santorini today still see this striking landscape, houses glowing white under the intense summer sun. But the color was not chosen for beauty alone. Ancient builders understood something important about heat. Dark stone walls absorbed sunlight and trapped warmth inside like an oven. White surfaces, however, reflected much of that solar energy back into the sky. So they crushed local limestone, burned it into lime, mixed it carefully with water, and painted their homes with the resulting white coating. The effect was remarkable. Even when outside temperatures climbed toward brutal summer heat, homes stayed noticeably cooler inside without electricity, machines, or moving parts, relying only on sunlight and simple physics. The reason this simple coating works comes down to basic physics. When sunlight strikes a surface, two things can happen. The surface can absorb that energy and convert it into heat, or it can reflect the energy back into the environment. Dark colors absorb most of the sunlight that hits them, which is why black asphalt roads and dark rooftops become extremely hot during the day. That heat then radiates into the building below, warming the air inside. White surfaces behave very differently. Instead of absorbing solar energy, they reflect a large portion of it away. Limestone and lime coatings are especially effective because their microscopic structure scatters sunlight in many directions, preventing heat from building up on the surface. The result is a powerful cooling effect. By reflecting sunlight before it can turn into heat, a simple white coating dramatically reduces the temperature of walls and rooftops, helping the entire building stay cooler throughout the day. In the 1970s, scientists decided to test whether this ancient technique actually worked under controlled conditions. At the Berkeley National Laboratory in California, researchers coated a flat rooftop with a simple mixture made from powdered limestone and water, essentially the same lime coating that Mediterranean builders had used for centuries. Nearby, another roof was left dark for comparison. As the sun beat down throughout the day, the difference became impossible to ignore. The white-coated surface stayed dramatically cooler than the dark roof beside it. In some measurements, the temperature gap reached nearly 40 degrees Fahrenheit. Even more important, the cooler roof prevented heat from transferring into the building below. Inside the structure, indoor temperatures dropped by several degrees, significantly reducing the need for mechanical cooling. The experiment confirmed what ancient builders had already understood through experience. Reflecting sunlight before it becomes heat can be one of the simplest and most effective cooling strategies ever discovered. As this simple cooling method proved effective, it quietly spread across many hot regions of the world. Along the Mediterranean coast, entire towns began to adopt whitewashed walls and roofs as a practical way to survive the intense summer heat. Places like Santorini in Greece, the coastal villages of Morocco, southern Spain, and parts of Italy all developed the same striking architectural pattern: bright white buildings reflecting the sun under cloudless skies. But behind the beauty was a practical purpose. These white surfaces helped reduce the amount of solar heat absorbed by homes during the day. By reflecting sunlight away, buildings stayed noticeably cooler inside, even during the hottest months. Over centuries, this technique became part of everyday life. Families would repaint their homes regularly with simple lime coatings, refreshing the reflective surface each year. Long before modern cooling systems existed, millions of people relied on this low-cost method to keep their homes comfortable in harsh climates. Everything began to change in the early 20th century when mechanical air conditioning entered the picture. In 1902, engineer Willis Carrier developed one of the first modern air conditioning systems designed to control temperature and humidity inside buildings. At first, these systems were used mainly in factories and large commercial spaces, but over time, they spread into offices, stores, and eventually private homes. Unlike the simple lime coatings used for centuries, air conditioning relied on complex machines, electricity, and ongoing maintenance. It required compressors, refrigerants, ducts, and constant energy to keep running. While the technology made indoor environments comfortable even during extreme heat, it also introduced a completely different model of cooling. Instead of a one-time, low-cost solution applied to a building's surface, air conditioning created a system that needed continuous operation. Homes no longer relied only on architectural design or reflective materials to stay cool. Many began depending on powered machines working around the clock to control indoor temperature. As air conditioning became more common throughout the 20th century, the way people thought about cooling began to shift. Instead of designing buildings to naturally resist heat, many structures were built assuming that mechanical systems would handle temperature control. Dark roofing materials, asphalt shingles, and dense urban surfaces became standard, even though they absorbed large amounts of solar heat during the day. At the same time, the cooling industry expanded rapidly, manufacturing air conditioning units, installing them in homes, supplying electricity, and maintaining these systems created a large and growing market. For many households, cooling was no longer a simple building feature. It became an ongoing service, powered by machines and energy consumption. Compared with this model, traditional lime coatings represented something very different. A low-cost method applied once to a roof or wall that relied only on sunlight and physics. As cities modernized, that older approach slowly faded from everyday construction, even though its basic cooling principle remained scientifically valid. Decades later, scientists returned to the same basic idea with modern technology. In 2021, researchers at Purdue University, led by materials scientist Xiaolin Ruan, developed an experimental coating that pushed the concept of reflective cooling even further. Their goal was simple: create the most reflective paint ever made. The result was extraordinary. The new formula was able to reflect about 98.1% of incoming sunlight, far more than typical commercial white paints, which usually reflect around 80%. Because so little energy was absorbed, surfaces coated with this material stayed remarkably cool under direct sunlight. In outdoor tests, the coated surfaces sometimes measured several degrees cooler than the surrounding air during the day. At night, the temperature difference became even larger. The research demonstrated that highly reflective coatings could provide powerful passive cooling without electricity, simply by preventing solar heat from building up on rooftops and walls. The cooling potential of highly reflective surfaces becomes even more impressive when researchers measure the total energy involved. In the Purdue experiments led by Xiaolin Ruan, scientists calculated how much cooling power a reflective roof could generate simply by reflecting sunlight and radiating heat back into space. For a roof area of about 1,000 square feet, the reflective coating could produce a cooling effect equivalent to roughly 10 kilowatts of continuous cooling power under strong sunlight. That level of cooling is comparable to the output of a typical central air conditioning system used in many homes. But unlike mechanical systems, this effect requires no electricity, compressors, or moving parts. The cooling happens passively through physics. By reflecting nearly all incoming solar energy and allowing heat to radiate away, the coated surface prevents the roof from heating up in the first place, dramatically reducing the amount of heat that enters the building below. As cooling technology expanded throughout the 20th and 21st centuries, entire industries formed around controlling indoor temperature. Today, the global paint industry alone generates well over $200 billion each year. Major manufacturers design coatings that balance durability, color variety, and cost while meeting modern construction standards. At the same time, the air conditioning industry has grown into another enormous market. Millions of homes rely on compressors, refrigerants, duct systems, and electrical power to maintain comfortable indoor temperatures during hot seasons. Manufacturing equipment, installation services, maintenance, and electricity usage all contribute to a massive global economic sector. Against this backdrop, traditional lime coatings represent a very different approach. A simple mixture of lime and water can be applied to a surface at extremely low cost and can last for long periods before needing reapplication. While not always suitable for every modern building type, the method highlights how passive cooling techniques can sometimes reduce dependence on complex mechanical systems. In many modern cities and residential developments, building appearance is regulated by architectural guidelines or neighborhood associations. These rules often determine what kinds of roofing materials, colors, and exterior finishes homeowners are allowed to use. In some communities, bright reflective surfaces or pure white roofs are discouraged because planners prefer uniform color palettes such as gray, brown, or earth tones. These darker materials can create a different thermal effect. Because darker colors absorb more sunlight, rooftops can heat up significantly during the day. That heat is gradually transferred into the building below, which can increase indoor temperatures and raise the demand for mechanical cooling. Urban planners and architects are increasingly aware of this issue, sometimes called the urban heat island effect. As a result, some cities have begun exploring reflective roofing standards or cool roof programs designed to reduce heat absorption. These efforts highlight how building color and surface materials can play a significant role in managing temperature in dense urban environments. Despite its advantages, lime coating is not a perfect solution for every building or climate. Compared with many modern commercial roof coatings, lime-based finishes can wear away more quickly under heavy rain, strong wind, or constant exposure to weather. Over time, the surface may gradually fade or thin, which means it usually needs to be reapplied every few years to maintain its full reflective effect. Historically, this was not considered a problem. In many Mediterranean communities, homeowners routinely refreshed the lime coating on their houses each spring. The process was simple, inexpensive, and often completed in just a few hours. A new layer restored the bright white surface and helped keep homes cool during the long summer months. Today, building owners may prefer longer-lasting synthetic materials that require less frequent maintenance. Even so, the traditional lime approach demonstrates how a simple, low-cost method can still provide meaningful cooling benefits when used correctly. For homeowners interested in trying this traditional cooling method, the process is surprisingly simple. The main ingredient is hydrated lime, a common building material that can be found in many hardware or construction supply stores. A standard bag is inexpensive and can cover a large surface area when mixed properly. To create the coating, the lime powder is combined with water until it forms a thin, milky liquid. A common mixture is about 1 part lime to 2 parts water, stirred until smooth. Once prepared, the solution can be applied to roof surfaces or exterior walls using a brush, roller, or sprayer. Most applications use 2 coats. The first layer is allowed to dry completely before adding the second. When finished, the bright white surface reflects a large portion of incoming sunlight. For many homes, the total material cost can be surprisingly low compared with other cooling upgrades. To understand how effective this method can be in real conditions, some homeowners have tested it themselves. In one example from Texas, a homeowner decided to apply a lime-based reflective coating to his roof during the peak of summer. Before the treatment, temperatures inside the attic regularly climbed to around 140 degrees Fahrenheit under the intense sun. After the roof was coated with the reflective lime mixture, the difference became noticeable within days. Measurements showed the attic temperature dropping to roughly 97 degrees Fahrenheit during similar weather conditions. With less heat entering the structure, the indoor living space also became noticeably cooler. Because the house absorbed far less solar heat, the air conditioning system needed to run much less frequently throughout the day. Over the course of the summer, the homeowner reported a significant reduction in electricity use, showing how reflective surfaces can directly influence household cooling demand. When comparing cooling methods, the difference in cost can be striking. Installing a new residential air conditioning system often requires a large upfront investment. Depending on the size of the home and the equipment used, installation can range anywhere from $5,000 to $15,000. After installation, the system continues to generate ongoing costs through electricity use, maintenance, and occasional repairs. By contrast, a reflective lime coating is far simpler. The main material, hydrated lime, can cost only a few dollars per bag, and a typical roof may require just a small number of bags to cover the surface. Application tools are basic, and the process can often be completed in a single afternoon. While lime coating does not replace air conditioning in every climate, it can significantly reduce the amount of heat entering a building. That reduction alone may help lower energy consumption and cooling expenses over time. Looking back through history, the idea behind reflective cooling is not new at all. Long before modern engineering, ancient civilizations had already discovered that controlling sunlight was one of the most powerful ways to manage indoor temperature. From the whitewashed houses of Greek islands to the lime-plastered buildings of the Roman world, communities learned through experience that bright surfaces could push heat away before it entered their homes. What modern science has done is simply confirm what generations of builders already understood. Experiments and new materials have shown that reflecting sunlight can dramatically reduce surface temperatures and lower the heat load inside buildings. Whether through traditional lime coatings or advanced reflective paints, the underlying principle remains the same. Across thousands of years, the solution has always been surprisingly simple. Reduce how much solar energy a building absorbs, and the interior becomes easier to keep cool even in the hottest climates. The knowledge behind reflective cooling never truly disappeared. In many parts of the world, especially across Mediterranean regions, traditional lime coatings are still used today to keep buildings comfortable during long, hot summers. What changed over time was not the physics, but the way modern buildings were designed and the technologies people relied on to control indoor temperatures. As cities grew and construction methods evolved, mechanical cooling systems became the dominant solution. Yet the basic principle discovered centuries ago remains just as valid today. Reflect sunlight before it becomes heat, and a building naturally stays cooler. In recent years, researchers and architects have begun revisiting these older ideas as energy costs rise and urban areas face stronger heat waves. By combining traditional reflective materials with modern building science, many experts believe passive cooling methods could once again play an important role in reducing heat and improving comfort in homes around the world. Understanding how simple design choices influence temperature can change the way we think about cooling our homes. Throughout this story, one idea keeps appearing again and again. Sometimes the most effective solutions are also the simplest ones. For thousands of years, people used bright reflective surfaces to reduce heat before it could enter their homes. Modern science has now measured and confirmed the same principle with detailed experiments and advanced materials. Today, as energy demand rises and many regions face hotter summers, these ideas are becoming relevant once more. Reflective roofs, lighter building colors, and passive cooling strategies are being studied as practical ways to reduce energy use while improving comfort indoors. If this story helped you see everyday materials in a new way, consider sharing it with someone who might find it useful. Sometimes rediscovering old knowledge can open the door to surprisingly modern solutions.